Their research has led them to the pinnacle of their fields, and they have the potential to transform our world. They are inventors, risk-takers, leaders. And tonight, the Academy of Medicine, Engineering, and Science of Texas honors these 4 innovators with the 2013 Edith and Peter O'Donnell Awards. Laura Hooper, Medicine. In her lab at UT Southwestern Medical Center, Dr. Laura Hooper is working to solve the mysteries of how our immune system copes with a staggering number of bacteria, more than 300 trillion that live in the human gut.
They do pose a threat. So these are bacteria. They have their own agenda, and they're in very close contact with the intestinal lining.
Laura's work focuses on identifying which proteins are doing the heavy lifting to protect the body from bacteria.
What sorts of proteins are made by the intestinal lining that might be important for keeping these bacteria from crossing into our tissues and causing disease? And so that led us to the discovery of a major group of proteins.
Within this group, Laura's team identified a protein called Reg3 gamma. Laura's research has shown that Reg3 gamma acts like a bodyguard, killing any bacteria that gets too close to human tissues.
We need our intestinal bacteria for our metabolic health, but again, like I said, they have their own agenda. So the trick is to dictate how close they can actually come to our tissues, and that's where Reg3 gamma comes in. It basically defines what we in my lab like to call the demilitarized zone in the gut.
When bacteria are able to cross this zone, problems ensue, like inflammatory bowel disease, which affects more than 1.5 million people in the U.S.
What Laura's been studying is very appropriate or very important to our understanding of how those diseases develop. And I think that Laura's research is clearly contributing to our understanding of what the normal processes are by which we regulate our commensal bacteria.
So how did the purification go?
Actually, I got a very good yield. So
Laura feels she's barely scratching the surface. Her goal is to find the next Reg3, another super protein that provides a stronger defense against disease.
One of the big pushes in my lab is to continue to try to discover new antibacterial proteins made by the lining, and we think it's going to be a particularly rich source of protein antibiotics that are not prone to have bacteria develop resistance.
Laura has established herself as a thought leader in her field. She's been named a Howard Hughes Investigator, an honor given to the top biomedical scientists in the country.
I can't say enough good about UT Southwestern. The quality of the science here is just outstanding, and I think it helps us all to raise our game.
Li Shi, Engineering. We look at today's technology and wonder, what could be next? When will efficiencies of size and speed reach a limit? Dr. Li Shi is on the forefront of finding answers to these questions, and his research in nanotechnology could have even broader implications, from transportation to treatments for cancer.
This is the temperature of what?
He's trying to advance how one is able to look at materials on the nanoscale and how the properties change, and if so, how can we use those changed properties in order to make something that's useful.
At his lab at the University of Texas at Austin, much of Li's work has focused on the heat generated by computer chips. Heat is a major barrier limiting the efficiencies of electronic and other devices, and Li may have found a material that can help. A thin layer of graphite called graphene.
Graphene has high conductivity. We only need to add a very small amount of graphene into the phase change materials. That's sufficient for us to extract the heat.
Li's findings suggest that electronic devices made with graphene will move heat away from hotspots more efficiently than copper or silicone. The result could mean smaller, more efficient devices that can handle more computing power. Li's lab is also working on a joint project to create thermal energy storage devices that would provide cabin heating and cooling for electric vehicles without draining the electric batteries. In addition, his team has been working on a semiconductor device for generating electric power from heat contained in the engine exhaust of a gasoline-powered vehicle.
If you can somehow utilize the thermoelectric device to convert even just 10% of the waste heat, you can use that to power the AC, for example, in the car.
And in the field of healthcare, Lee is partnering with biomedical researchers to use nanomaterials in the area of drug delivery.
We want to use that technology to control the size and shape of those nanoparticles so that there's a higher chance the cancer cells will eat them. So then it can help to kill just the cancer cells.
Despite Lee's far-reaching research, ultimately his work comes down to one thing: teaching.
I think that's the most enjoyable part of the research, is actually being a teacher, scholar, doing things that can one day probably change the world.
Yujing Zhang, science. How we think, walk, and run is all tied into the precise movement of proteins across cell membranes. At UT Southwestern Medical Center, Dr. Yujing Zhang is working to solve the mystery of how these specific protein movements, called protein transports, impact the body and their role in disease.
Did you get crystals?
Yes, I'm going to show you later.
Okay, big, nice one.
Using X-ray crystallography, Yujing's team is able to study what protein pathways look like under varying circumstances.
So how about the other crystal form?
These three-dimensional crystal images allow Yujing and his students to identify disruptions or imbalances in protein transport, which can result in abnormalities like heart arrhythmia. Yujing believes the more we know about these movements, the more likely scientists can develop treatments to fight these disorders.
Once you know the fundamental properties of a protein, it will help when you move on to more sort of practical questions.
To correct, say, an arrhythmia, a cardiologist will prescribe a medication that affects the movement of calcium ions in or out of the heart cell, and the way that those calcium ions get in and out of the cell is in part through the proteins and the class of proteins that Dr. Zhang studies.
One of Yujing's most notable breakthroughs is in his research of a protein labeled the big potassium channel, a potential target for drugs that could treat stroke symptoms and movement disorders like multiple sclerosis.
Eventually, we're going to slowly moving towards more sort of medical relevant proteins, like human channel proteins. Once we have that, we can use so-called structure-based drug design to find the blocker or some modulator to change the function of the protein. It's our eventual goal.
Yujing credits the impact of his mentors for enabling his success, including Nobel Prize winner Rod McKinnon. Now, as his work gains wider relevance in a whole range of disciplines, Yujing has become the one making the impact.
His work is not only of interest to the protein biochemist or to the electrophysiologist, but also it has great practical applications. It ranges from cardiology to neurology to disorders that affect movement. All target these class of proteins that he works on.
Tim Nedwed, Technology Innovation.
And I'm going to test it against our new dispersant.
For more than a decade, Tim Nedwed has been working on innovative solutions for treating oil spills. The leader of ExxonMobil upstream research company's oil spill response program was ready when a potential disaster struck in the Gulf of Mexico.
Tonight, there's a state of emergency in effect in the state of Louisiana.
The Deepwater Horizon spill gushed from the seafloor for 3 months and may have released between 20 to 50,000 barrels of crude oil a day into the Gulf.
It just makes sense, rather than letting the oil come up to the surface and having to find it and inefficiently treat it with dispersants. If you're going to use dispersants, put it at the source exactly where you know the oil is.
Tim's research suggested that injecting dispersants into the spill's source rather than on the surface would break the oil into small droplets that would biodegrade in the water column to keep oil from reaching the surface and fragile Gulf Coast shorelines.
knowing the guys that were on the ground waiting for that oil to come in and telling me that, gosh, we just aren't seeing the oil, that's when I knew, and that was a few weeks into the spill. We did something important.
This new approach is not only credited for lessening the amount of oil that reached the shore, but also limiting the amount of potentially harmful vapors that reached response workers on the surface.
He took his years of experience in research, and in a time of very high pressure, he came up with a solution that impacted a lot of people in a very significant way.
Now, as a result of Tim's efforts, the equipment needed for subsea dispersant injection is being installed in oil-producing regions around the world. Tim's next challenge? Developing new ways to treat oil spills in the freezing waters of the Arctic, which includes, among other ideas, a concept for controlled burning of oil using herding agents to thicken slicks without booms. This allows igniting and burning oil from helicopters instead of boats. The speed of a helicopter-deployed response option could fundamentally change industry's approach to oil spill response in all areas and not just the Arctic.
We try to do things to make our ability to respond to oil spills better, but our hope is to never use them.
Congratulations to the 2013 recipients of the Edith and Peter O'Donnell Awards.